Welcome. This presentation is titled Realistic HDFS Deployment Scenario, a Practical Guide to Enterprise Hadoop Distributed File System Implementation, authored by a Big Data Solutions architect. Let's begin with an introduction. HDFS, or the Hadoop Distributed File System, is a distributed file system designed for storing and managing massive datasets, typically ranging from hundreds of terabytes to multiple petabytes. It is built to run on clusters of commodity hardware, with a typical deployment consisting of 50 or more nodes. Its key characteristics include built-in fault tolerance, achieved primarily through data replication, high throughput for reading and writing large files, and immense scalability, supporting clusters of over 10,000 nodes. HDFS operates on core principles. First, moving computation to where the data resides is cheaper than moving the data itself. Second, it's optimized for a write once, read many access model. And third, it automatically handles fault detection and recovery. For a real-world sense of scale, consider a healthcare system that uses HDFS to process over 50 terabytes of patient imaging and record data every single day. Before any installation, careful planning is critical. You must consider several factors. First, your data volume and its projected growth rate. Industry insight suggests business data doubles every 1.2 years. You must also understand your file size distribution, as HDFS is optimized for large files. Performance requirements must be defined in terms of throughput, say in gigabytes per hour, and latency for data access. Compliance is non-negotiable. This includes data encryption, both at rest and in transit, and adhering to regulations like HIPAA for healthcare or GDPR for data privacy. Robust authentication and authorization frameworks are a must. Finally, assess your existing infrastructure, network capacity, rack configuration, and the potential for reusing older hardware to control costs. Hardware planning is about right-sizing each component. The name node, which manages the file system metadata, requires significant RAM. A good rule of thumb is 1 GB of RAM for every 1 million files stored. We recommend 64 to 128 GB of RAM configured with RID for redundancy and dual power supplies. Data nodes, where the actual data is stored, should have 12 to 24 CPU cores, 64 to 128 GB of RAM, and use JB or D, just a bunch of disk configurations for 12 to 24 TB of raw storage per node. The network is the backbone of the cluster. 10 of 40 GB Ethernet with redundant top-of-rack switches is essential. A typical rack holds 20 to 30 nodes. For a storage example, a raw capacity of 480 terabytes with a replication factor of 3 gives you 160 terabytes of usable space. Factoring in file system overhead, your effective capacity is approximately 112 terabytes. Selecting a stable and supported software stack is foundational. For the Java development kit, we recommend OpenJDK 11, a long-term support version. The operating system should be a robust enterprise-grade Linux distribution, such as Red Hat Enterprise Linux, CentOS 7 or newer, or Ubuntu 18.4+. For file systems, use ext-4 for the operating system drives, and XFS for the data drives due to its superior performance with large files. For Hadoop itself, version 3.3.6 or newer is recommended to leverage critical features like erasure coding for storage efficiency, enhanced security, and performance improvements. A quick tip: disable the no timeout option on your data disks to prevent unnecessary write operations and boost speed. A robust deployment architecture ensures reliability and performance. A common topology involves 3 racks for 4 rack awareness. The name node is placed in a dedicated rack for isolation and protection. 36 data nodes are distributed evenly across the 3 racks. Data is replicated with a factor of 3, and the placement policy is rack-aware. This means one replica is on a local node, another is on a different node in the same rack, and a third is on a node in a different rack. This protects against both node and rack failures. For high availability, we configure active and standby name nodes managed by a patch as your keeper. This setup ensures an automatic failover in less than 60 seconds if the primary name node fails. The installation process is methodical. First, create a dedicated Hadoop user account on all machines for consistent permissions. Then, install the required version of the JDK. Next, configure SSH for passwordless login between all nodes in the cluster. This allows the Hadoop scripts to manage nodes seamlessly. Then, download the Hadoop version 3.3.6 package and install it on all nodes. Finally, set the necessary environment variables such as JAVHOME and HDOOPHOME in the bash or C file of the Hadoop user to ensure they are available in every session. Configuration is done through XML files. The course site XML file defines core properties, most importantly FS, default FS, which is set to HDFS//namenode 9000 to tell all clients where to find the name node. In HDFS site XML, you set HDFS specific properties. This includes the replication factor, DFS replication equals 3, and the directories where the name node and data nodes store their metadata and data. The YARN site XML configures the resource manager. Here, you might define the scheduler, like the capacity scheduler, and tune it to handle a high number of concurrent applications, up to 10,000. Ongoing cluster operations are key to health. You must continuously monitor the name node's health and its storage usage, keeping it below 80%. Watch for missing or under-replicated blocks. Check data nodes for disk health, ensuring no failed drives, monitor storage capacity per node, and verify network throughput. Tools for this include the built-in Hadoop web UIs or more comprehensive solutions like Apache Ambari, Cloudera Manager, or custom monitoring scripts. Regular maintenance includes running the balancer to redistribute data evenly, performing rolling restarts for updates to avoid downtime, and planning for seamless capacity expansion. In an enterprise, security is layered. For authentication, integrate with Kerberos or Lightweight Directory Access Protocol, LDAP, and Active Directory. Authorization controls who can do what. This is managed through POSIX permissions and enhanced with frameworks like Apache Ranger or Sentry for fine-grained access control. Data must be protected through encryption, both at rest and in transit. For sensitive fields, data masking may be required. Finally, comprehensive auditing through detailed logging, integration with a SIEM system, and regular compliance audits is essential. This is especially critical in healthcare for protecting PHI or protected health information. To optimize performance, start with the HDFS block size. For large datasets, increase it from the default 128 MB to somewhere between 256 MB and 1 GB. Tune the JVM heap sizes, allocate 16 to 32 GB for the name node and 8 to 16 GB for each data node. Handler counts are crucial for concurrency. Set DFS name node handler count to between 1 and 200 and the data node handler count to 30 to 50. Optimize data locality by co-locating compute and storage and use YRN's rack OS scheduling. For benchmarking, expect 100 to 200 MB per second per node. For scale, consider Yahoo's cluster, which managed over 400 petabytes of data. HDFS powers transformative use cases across industries. In healthcare, it analyzes patient data to predict heart attack risks. In finance, it runs complex risk models and detects fraudulent transactions in real time. The retail sector uses it for deep customer analytics and optimizing inventory supply chains. Telecom companies rely on it for predictive maintenance on network equipment and planning capacity. Even governments use it for crucial tasks like modeling disease outbreaks to anticipate pandemics and analyzing vast datasets for tax compliance. In summary, adhere to these best practices. Start with a pilot cluster to learn and validate. Enable monitoring and alerting from day one. Define a clear data governance policy and always plan for data growth. Document your operational procedures, automate deployments where possible, and invest in training your staff. Finally, avoid common pitfalls, underestimating name node memory needs, skipping regular balancer runs, using underpowered or unreliable hardware, and neglecting network planning. For further learning, please consult the Apache Hadoop official documentation, the HDFS architecture guide, articles on Linux file systems for HDFS, the detailed Hadoop installation guide, and papers on real-life use cases of Hadoop. Thank you for your time and attention.